Welcome everyone to this explainer. You know, geometry can sometimes feel like this endless, confusing maze of rules and equations, but honestly, it really doesn't have to be. Today, we're going to take the core principles of quadrilaterals and turn them into a simple, incredibly easy-to-use toolkit. By the end of this, you'll be able to look at a shape, spot the hidden clues, and unlock literally every single missing variable with total confidence.
Okay, let's dive right into our roadmap for today. We've got 4 main stops. First, parallelogram angle properties. Second, solving unknown variables. Third, we'll look at sides and perimeters. And finally, we'll wrap up with special quadrilaterals.
So starting right off with number 1, parallelogram angle properties. These are what I like to call the golden rules.
To really master parallelograms, we need to define their absolute unbreakable laws. First up, we have adjacent angles. These are the angles right next to each other. Their golden rule, they're supplementary. That means they will always, without fail, add up to exactly 180 degrees. Second, we have opposite angles. These are the ones sitting directly across the shape from one another. And their rule? They are always exactly equal. You're definitely going to want to keep these 2 master keys in mind because they're going to unlock almost every puzzle we look at today.
Let's actually put those rules into action. Just imagine a parallelogram where we only know one single detail. Angle A is 110 degrees. Well, because angle A and angle B are adjacent, they have to equal 180 degrees together. So subtracting 110 from 180 instantly tells us that angle B is 70 degrees. Now we just use our second rule. Opposite angles are equal. Angle C perfectly mirrors angle A, so it's 110 degrees. And angle D perfectly mirrors angle B at 70 degrees. See? With just one starting number, we unlocked the entire shape.
All right, moving right along to section 2, solving unknown variables. Or, as I like to think of it, tracking down x.
Let's transition to the next level of complexity here. We don't have nice, neat numbers anymore. Instead, let's say we're told 2 adjacent angles in a parallelogram are 3x minus 4 degrees and 3x plus 16 degrees. Okay, it looks kind of intimidating, right? But challenge yourself for a second. How do our 2 golden rules actually apply to algebraic equations like this? And this brilliantly illustrates how that simple rule of adjacent angles effortlessly sets up our algebra. Because the angles are adjacent, we know they absolutely must add up to 180 degrees. We just add the 2 algebraic expressions together, so 3x plus 3x gives us 6x, and a negative 4 plus 16 gives us positive 12. Set that whole thing equal to 180. Subtract the 12, leaving us with 6x equals 168. Divide by 6, and boom, we discover our elusive variable, x equals 28.
And here is the really satisfying payoff. We don't just stop at x. We plug that 28 right back into our original equations. For angle A, 3 times 28 minus 4 gives us exactly 80 degrees. For angle B, 3 times 28 plus 16 gives us 100 degrees. Notice anything there? 80 plus 100 is exactly 180. Our adjacent angles check out perfectly. And of course, because opposite angles are equal, angle C has to be 80 degrees and angle D has to be 100 degrees. The geometry proves the algebra, and the algebra proves the geometry. It's awesome.
Up next, section 3, sides and perimeters. Let's explore the outer boundaries. Let's step outside the shape for a minute and look at a totally new scenario. We know the total outer boundary, the perimeter, is 140 centimeters. We're also told one side is 10 centimeters longer than its adjacent side. So how do we unlock this puzzle when we don't actually have a single specific length? The key is remembering the core property of a parallelogram's sides, which is that opposite sides are always equal. Let's formulate our equation. We're going to set the shorter side as our unknown x, which makes the longer adjacent side x plus 10. Now here's where the geometry magic happens. Because opposite sides are equal, we have 2 sides that are x and 2 sides that are x plus 10. Adding all 4 of those sides together equals our total perimeter of 140. Combining all our x's gives us 4x, and the numbers give us 20. Subtract 20 to get 4x equals 120, divide by 4, and we hit our target, x equals 30.
So the crucial point here is that defining our unknown x clearly makes identifying all 4 side lengths incredibly simple. Our short sides, which we just called x, are 30 centimeters each. Our long sides, which were x plus 10, are exactly 40 centimeters each. And honestly, the best part? We can instantly check our work. 30 plus 40 plus 30 plus 40 perfectly matches our starting perimeter of 140 centimeters.
Finally, we arrive at section 4, special quadrilaterals. Let's talk about rectangles and rhombuses.
Now let's see what happens when basic parallelograms evolve into shapes with very highly specific features. A standard parallelogram has opposite equal sides and opposite equal angles. A rectangle keeps those opposite equal sides, but strictly enforces a new rule. All four angles must be 90 degrees. But I really want you to focus on the rhombus. It demands that all four sides are exactly equal, and it has an incredible hidden feature. Its diagonals, the lines drawn from corner to opposite corner, they bisect each other at exactly 90 degrees, forming a perfect crosshair right in the middle.
Because of that special feature, we can tackle classic boss-level geometry questions. Imagine a rhombus, where the only thing we know is that its inner diagonals are 16 centimeters and 12 centimeters. From just those lines on the inside, we need to find the length of the outer side. To do this, we have to combine our geometric properties with another incredibly powerful mathematical tool.
And that secret weapon is the Pythagorean theorem. As a quick refresher, this theorem states that in a right-angled triangle, the square of the long side, the hypotenuse, is equal to the sum of the squares of the two shorter sides. This is absolutely the ultimate tool for solving rhombus diagonal questions, because remember, the diagonals of a rhombus always meet to form perfect right-angled triangles.
Let's break down the math on this one. We know the diagonals cut each other exactly in half. So our 16-centimeter diagonal gives us a half length of 8 centimeters, and the 12-centimeter diagonal gives us a half length of 6 centimeters. These two halves naturally form the base and height of a perfect right-angled triangle tucked right inside the rhombus. Applying Pythagoras, 8 squared plus 6 squared will equal the square of our outer side. 8 squared is 64, 6 squared is 36, 64 plus 36 equals 100. And finally, what number multiplied by itself is 100? The square root is 10.
Now, what's really interesting about this result is the final reveal of our 10-centimeter side. Because this shape is a rhombus, solving for just one side means we've instantly found all four. All the outer boundaries are exactly 10 centimeters, perfectly derived from the inner diagonals meeting at 90 degrees. It's just an incredibly satisfying puzzle to solve. And that brings us to the end of our roadmap. As we've seen throughout this explainer, the rules of geometry, whether it's adjacent angles, equal opposite sides, or intersecting diagonals, they aren't just arbitrary obstacles to memorize. They are a structured toolkit. They are the keys that let you look at the unknown, track down variables, and confidently solve the mystery. So look around your world, apply this logic, and I just have to ask, what unseen variables will you solve for next?